Hello, my name is Valeria Sirota. I work at the Theory Department of Lebedev Physical Institute, and the topic of my talk is cosmology. Cosmology is the history of the universe. It studies the evolution of its oldest objects and the space and the evolution of the space itself. We have not much information on the subject, so here are the three main sources of information we have got. This is the hierarchical structure of the universe, its expansion, and the cosmic microwave background radiation. In this talk, I'll try to tell about them all and also to discuss the main results of cosmology for the last decades. These are dark matter and dark energy. The first source of information is the hierarchical structure. These points and little spots there are not stars, they are galaxies. We have been studying them for about 2 centuries and they still make surprises. Galaxies are also not distributed homogeneously in the universe. Many of them are gathered in groups and individual galaxies together form clusters. In turn, 10 to 100 clusters are combined to make superclusters. The whole sequence of embeddings is called hierarchical structure. Studying this hierarchical structure, one can make some conclusions about its evolution. For example, the end of the table is just the end of this hierarchical structure. There are no superclusters. There are no lines below the superclusters. Why? Because the age of all these structures is limited, and the greater structures just have not had time to form. If we consider a cluster and measure positions and velocities of different galaxies in it, we can calculate the mass of the cluster. And the amazing thing is that the mass of the cluster turns out to be many times greater than the sum of the masses of all galaxies and gas clouds and dust clouds in it. So there is something that is very heavy and absolutely invisible. The same thing happens to galaxies. If we consider some distant cloud of gas that is far away from the center of a galaxy, even much farther than the edge of the galaxy, and measure its orbital velocity, one expects that the velocity of the cloud decreases as a function of the radius, just as it follows from the second Newton's law. In fact, the situation is quite opposite. For most part of the galaxies, the orbital velocities do not decrease at all as a function of radius. The velocity remains almost the same for about 10 radii of the visible part of galaxy. What does this mean? It means that the galaxies are embedded in giant halos of invisible but very heavy matter. The mass of the halos is about 100 times greater than the mass of the visible galaxy. So the most part of matter in the universe turns out to be invisible. And this invisible matter is called dark matter. What does this dark matter consist of? There are 2 main classes of hypotheses. The first hypothesis is that the dark matter is made of planets like Jupiter's and faint stars. In this case, this is usual baryonic matter consisted of protons and electrons, but it is just gathered in such forms that it is invisible. This hypothesis seems simple, but in fact, there are a lot of questions that are very difficult to answer. For example, how did all these planets and stars appear in the middle of nowhere? And why do there appear only faint stars and no bright ones? These questions are very difficult to answer, and besides, all these candidates are practically excluded by the observations of Hubble Space Telescope. If there were stars or planets, we would already see them. So probably they are not there. The second kind of hypothesis assume that the dark matter consists of some absolutely new particles that we have not ever seen or detected before. These are not protons and electrons. This is not a usual matter. This is something absolutely new. We have different theories that predict different kinds of particles to be candidates for the dark matter, but these are only theories. We have no definite understanding what it is at all, so we do not know what it is. The second source of information is the expansion of the universe. This picture is abstract and doesn't mean anything, but I hope that everybody knows that our universe is expanding. What does this expansion mean? How can we understand it? The subject is essentially relativistic, but to get some idea of what happens and even to get some right relation, it is convenient to consider a simple Newtonian model for the effect. Consider a homogeneous ball and blow it up in such a way that the layers do not mix during the expansion and the density remains homogeneous during the expansion. There are two possible scenarios for the evolution of this ball. It can either continue to expand infinitely, or at some moment the expansion stops and the ball begins to recollapse. There are also two possible scenarios for the evolution of the universe that we have in general relativity theory. But the most likely scenario for what happened to our universe is the third intermediate case. In our classical model, this means that the energy of each particle of the ball is zero. In this simple case, you can easily check that the radius of the ball and all the distances inside the ball will obey the power law, and the density of the ball remains homogeneous. And also the velocity of each point of the ball is proportional to the distance from the center, which is called Hubble law. All these properties preserve in the general relativity theory. But there is only one thing that cannot be understood in the frame of the Newtonian model. This is a complete symmetry of the expansion. The expansion of the universe is homogeneous and is isotropic. It is just the same at any point of the universe. While in our ball, we always can see the boundary of the ball, and we always can distinguish between the center of the ball and the point somewhere near its edge. It's very difficult to imagine a three-dimensional homogeneous and isotropic expansion, but it is easy to understand looking at the spaces of smaller dimension. For example, imagine two-dimensional people living in the two-dimensional surface of this balloon. Let the balloon expand. What would the people observe? They would see that all the distances between any 2 points of their world are increasing as a function of time. And all the points of the sphere are in the same conditions. But they do not see the center of the expansion, because the center of the expansion doesn't belong to the sphere. The same situation happens to our universe. We see the homogeneous expansion, but we do not see the center of the expansion because it doesn't belong to our three-dimensional space. But how do we know that the universe is expanding? This is just like the Doppler effect. If you see a source of light that is moving away from you, then you observe that the frequency of the light is lower than it should be, and its wavelength is greater than it should be. So the light of the source would be redshifted. The same thing happens to the galaxies. We see that the light of distant galaxies is redshifted, and the more distant is the galaxy, the greater is the redshift. The other thing that is well defined is the luminosity of standard candles. Standard candles are some kinds of stars for which we know their absolute luminosity, that is, their power. And measuring the energy that comes from these stars to us, that is luminosity, we can conclude how far these candles are. So cosmologists measure the luminosity as a function of the redshift instead of velocity as a function of distances. And analyzing this function, one can derive the expansion rate of the universe and its evolution. And the amazing news is that the expansion of the universe appears to be accelerating. It looks like as if something inside the ball would push the layers away instead of attracting them. No one kind of matter we know, and even no one kind of hypothetical particles or particles we can imagine doesn't possess this property. The gravitational action of any matter is always attraction, and matter cannot push something away by its gravitation. So it is not energy at all. So we call this dark energy. Nobody knows what this dark energy is, and nobody understands it completely, but one of the conventional ways to understand it is that it is the energy of vacuum. Why vacuum? Because if we take some matter and start to expand the volume in which it is, then the energy of this matter would either conserve or decrease for any kind of matter. But for dark energy, it increases proportionally to the volume. You double the volume and the energy is twice as much. What is the thing? If you double the volume, its amount doubles too. It is nothing, it is just emptiness. And the emptiness is vacuum. So the dark energy is the energy of vacuum. Last but not least is the cosmological microwave background radiation. Here you see the map of this radiation all around the sky, or to be more precise, the map of its fluctuations. The fluctuations are very small and the background radiation is highly isotropic. And the same situation happens in any point of the world. Everywhere there are many, many photons traveling in all directions. The number density of photons is about 10 to 9 times greater than the number density of protons and electrons. They are rather cold, but it's because they are very old. As the universe expanded, the wavelengths of all photons increased proportionally to the scale of the universe, and so their temperature decreased. In the past, this photon gas was very hot and very dense, and the matter was also hot and dense, and it was ionized. There was plasma, consisted of protons and electrons, and it interacted very strongly with these photons because free electrons scatter photons very effectively. So there was such a soup consisted of photons with small admixture of protons and electrons. All of them had the same temperature, and it cooled down gradually, and its temperature and pressure were governed by the photons. And so it happened until the temperature became 4000 degrees. At these temperatures, protons and electrons started to couple into hydrogen atoms, and then the interaction between matter and radiation stopped because there were no more free electrons, and the electrons in hydrogen do not scatter photons. So after recombination, the thermodynamic equilibrium between photons and baryonic matter stopped. So every photon of the cosmic microwave background carries with it information of its last scattering that happened at the epoch of hydrogen recombination. So the map of the CMB is just a photo of the universe at the time of recombination. The small-scale anisotropy in this photo is the subject of intensive studies. So the fluctuations of matter at the recombination epoch were so small, and only 14 billions of years have passed since then. So the galaxies and clusters of galaxies and so on have not had enough time to form, to grow up. Something should have helped the galaxies to form. Their own gravity was not enough for that. And here again, we can remember the dark matter particles. If the dark matter does not interact with the baryonic matter or interacts very weakly, then it would decouple or leave the thermodynamic equilibrium much earlier than the baryon matter do. So they would have enough time to form the galactic halos, and the baryon matter, after recombination, could just fall down in the potential wells that are previously formed by the dark matter. So probably the dark matter helped the galaxies to form. This is only a hypothesis, but it is the only hypothesis we have. To summarize, from the CMB data and the data on expansion rate of the universe, we get such a distribution of energy in the universe. The visible matter, stars, planets, gas, dust, everything we see and detect, makes only about 5% of the whole energy of the universe. This 5% is all we know. The dark matter, consisted of unknown hypothetical particles, makes about 25% of the whole energy. And all the rest is the dark energy. Please don't confuse dark matter and dark energy. Dark matter is non-uniformly distributed. It acts the dynamics in galaxies and clusters of galaxies. And it probably caused the formation of galaxies and clusters. The dark energy is uniformly distributed. It does not act at the scales of galaxies at all. It acts only at the extremely large distances. And it pushes the universe away, accelerating its expansion. To finish this talk, I'd like to show you this very brief list of what happened to the universe during the last 14 billions of years. You can see that we have discussed here only less than half of this list. But you can always use another sources of information to know more. So good luck, and thank you for your attention.